Okay. Uh, Today's class, we'll just quickly recollect of what we have seen in the previous class, and then we'll move on to the consequent topic. To start off with, we were trying to discuss on morphological analysis, but before understanding or analyzing the morphology, we are also expected to understand the basic terminologies um, which were part of natural language processing and the morphological analysis process and the way in which finite state machines are used in the analysis phase. To start with, we were talking about the terminologies in morphology. Mainly, we need an analysis in the morphological morphology just to understand how the words are been built in so that we'll be able to process it in the right notion as well as we'll be able to generate it because machine learning and processing is one part where you need an clear understanding and the other one is language generation where natural language has to be generated from based on the concept of understanding and therefore it is required to create meaningful sentences and the sentences which comes from the vocabulary which are already defined and so morphological analysis plays a very major role which they call it as parsing. Parsing is where you try to write a set of rules which actually has a left hand side and a right hand side and then you try to derive those rules derive things with the help of those rules so that you form the correct words and there are two ways in which one second. So to recollect, we were talking about the morphemes, which are the basic units which gave the meaning. And the way in which the morphemes are arranged, you call it as phoneme, and the way in which the meaning which are given to it is termed as sememe. So there are morphemes which gives you the same meaning but cannot be replaced with one another, which you call it as the allomorphs. And then you have free morphemes which have their meaning by itself. They stand alone but then given meaning, whereas bounded morphemes has to join with the free morphemes to given meaning. The bounded morphemes again were divided into two. If by adding a prefix or a suffix or both, if it could if it could indicate a word from a different class. For means a noun can be converted to a verb or an adjective, so on and so forth, or vice versa. Then you call it as derivational morphemes. But then if it is converted to either singular or it takes in different tense, then you call it as inflectional morphemes. We also have different types of morphemes based on the properties, on how they are joined, how they are sliced, how they are being converted, so on and so forth. So we have a lot of terms. This is what we were talking about in the previous class. To be more specific, morphology processing has various terminologies or the phases. The first one is lemmatization, where you talk about a word and you try to produce different meanings out of it. So, saw can be a past tense of see, or saw can be a noun which talks about the saw itself. So, what does a morphological analysis do? It tries to generate the word along with the past tense or noun, or whether it's a singular, plural, and so on and so forth. And then we try to fix in and we try to generate it. So we also talk about word formation because that is one main part which is required when you go in for a natural language generation. And then comes the various process of it. And then the next part, what we were trying to discuss was morphological analysis, where you can now just look at these things, where you have cat. which is considered as a noun. So now for noun, we'll use it as plus n. And for plural, it is plus pl, verb, it is plus v, so on and so forth. So here it is taken, cat is the morpheme, which is a noun, and cats, it talks about a plural. Here, cat, you talk about noun and singular, noun and plural, so on and so forth. Now, here you have goose, so it has two outputs. Either it can fit in with goose, which is noun, or goose, which is an verb. And then, so it gives you all such kind of outputs. And now the issue involves saying when you have y, if I have to talk about a plural, for boy it's yes, and y, fly, it becomes ies. Now the rule is y, whenever you have y at the end of the morpheme and it is converted to plural, it has to be converted to I. But that doesn't work everywhere. You have to talk about the character previous to Y. If it is a vowel, we'll take it as such. If it is a consonant, we'll convert it to IES. So such kind of rules has to be clearly represented. Many things cannot be generalized because different constraints are being added as and when we work on. And therefore, while doing morphological analysis, we move in terms of representing them in finite state transducers. So now, before moving on, we'll just identify. You start with the first. What is the finite state? I'll just move here and then we'll come back. What is finite state transducer? Is a finite state machine which consists of different states, and on every character you move from one state to the other. Fine. Now this finite state machine is one where we talk from, we discuss this concept from theory of computation, or it comes from the basic computational informations. So finite, why do we call it as finite state transducer? In general, finite state automaton is the keyword what we use, or a finite state machine. Now, this finite state machine has a set of states. On reading every character, you start from the initial state and you end up in any one of the final states. And when you reach the final state, the finite state machine can produce two outputs. Either it can say whether the string is accepted by the machine or the string is not accepted by the machine. Or the other way around is it can also produce an output other than yes or no. If it just says yes or no, or the if it just says whether the string is accepted or not accepted by the machine, you call the finite state machine as finite state acceptor. Whereas if it can produce any other output other than yes or no, you call it as a finite state transducer. So to start off and to combine, you know what is morphological processing. It tries to recognize the term by breaking down into simpler morphemes. That is what is meant. Okay. So this is what is given here. It takes in the problem of recognizing that foxes breaks down into two morphemes, fox and es, and then you map it accordingly. Fine. So here it talks about the cat, which is noun and plural, where you can talk about goose, which gives in two information. Now I am supposed to choose one among these two, which perfectly matches into that particular constraint. So we are again talking about inflection and derivation. Inflection by adding a particular morpheme, a prefix or a suffix. If it give me the same class, but then in a different tense or in a different number format, then you call it as inflection. But if it gives you a meaning which produces which sorry, if it gives a word which gives you a different class altogether, then it is really hard to predict the meaning. and therefore this finite state transducer is really going to be tricky. Now, here is an example of regular forms, regular verbs, and irregular verbs. We all know about these regular and irregular verbs because these regular verbs have four morphological forms, which talks about the main part of the word, which you call it as a morpheme. And here it is termed as stem. The root word is termed as stem. We talk about plural, the continuous form and the past form or the participle. Whereas when it comes to irregular, you do a lot of changes. And here you know just by adding yes what happens, the ing what happens, and past tense ed what happens. Whereas when it comes to the irregular form, you have a lot of changes to be made. So when you have a lot of different changes which has to be made, then we go in for having more number of rules. Now, here is an example of the derivational morphology where a verb is converted to a noun. All these are verbs and adjectives which is converted to a noun part. And a noun, verb, or adjective is converted to an adjective part. Now comes the more finite state automata. Now, just take this particular example. Just take this example. You have clever, you have various names onto it. Okay, we have various names onto it. The first one is clear. So this become the first state becomes the initial state. And by reading character, if you just they have taken in one, two, three, four, five, I think five words together. One, two, yeah, four words. It is clear, clever, and then it goes on with ever, year, fat and father. All these things are being given to you. So now what happens? It's these two starts with C. So you have on C, it moves on to a single state as output, and the next two characters are L. So they again go on with L, and then it is E. So you have E, and where the changes come is here. It is AR. Here it is BER. AR moves on to the final state. Always a final state will be represented by two circles, double circle. Whereas the initial state, you start from nowhere. Whenever you go on to a finite state automata, you will have a single initial state but multiple final state. The reason is the starting point is the same. As and when you read the characters, you move on and end up in different finite final states. And when it is E, it moves on directly here, and you have these two, that's the third and the fourth word, which starts with E and after which it changes. So you have EAR and VER as such. And the next one, the last two words you talk about, the first three characters are the same. So you have FAT and final state. You need not stop in the first final state you encounter. You can move to any other final state if it's possible. In this case, if I have a character after T, I'll move on to this particular position. So if I have FAT, I'll stop here and say that the word is accepted and the word what has been read is fat. But if I am going to read father and then I'll say FATHER, and you end up over here, okay, and say a father has been accepted or it has been generated. This finite state automata has a set of rules, has different form of representation, but here what we see is a graphical representation where you have a set a lot of nodes which you call it as states, and the edges which are based on the symbols what you read. Now for an morphological analysis, most probably we have all the 26 alphabets along with the terminologies such as noun, plural, and so on and so forth of what we read over here. Now, what do I need to have to build an morphological parser? The first one is lexicon, which talks about the list of root words, the prefix and the affix which can be added. So I have to have a clear understanding of all these three. And the next one is the order in which these things can be combined. Sometimes a noun can be combined with an yes if it's plural, but for plural, I cannot have it on to the left. So that is how it works on. So the order in which these root words and the affixes has to be combined should be known to us. So the first one is the list of stems and the prefix and the suffix of which we have to add in, and the second one is the way in which these has to be combined. Now how do I combine all this is based on certain rules, which here we call it as the orthographical rules. One second. Which here we call it as the orthographical rules. Any rule as such will have a left hand side and a right hand side. When I say y produces IE, this is where you talk about the try. For example, you have try and you convert it to a plural. If it is a plural, I have to have an yes. Okay. So try, we call it as a verb. So I have another form plus v. And then it becomes you have to represent plural. We'll take it as PL. Now, when this is given, I'll have a rule saying when y is combined with the plural, okay, y has to get converted to IE. So what happens the next one, y gets converted to IE and then you have s to be added. So this whenever you have a left hand side and the right hand side, and in the way of deriving, that is what you call it as parsing. Parsing is where you start with the initial part and you end up with the string or the sentence where you can produce it. So, on the way of parsing, whenever you have a rule and you find the left hand side in that intermediate step, I can replace the left hand side by the right hand side. So, why step number 5, I would like to, I have encountered try and I find y is present. And in step number 6, it becomes TRIE. So, that is how the substitution happens. So now, a lexicon is a repository of words. We know about it. And how do I model it? Is this way. Q naught is the initial state if it is a regular noun. Now, for noun, you have taken two things. One is a regular noun, and the other one is a irregular noun. Irregular noun, I cannot add yes for in plural. You only talk about the noun and the numbers. Okay. So any noun is a regular noun or an irregular noun. Irregular noun, I cannot add an yes to it. So now what happens if it is a regular noun and a singular? Q1 is my final state. And if there is a regular noun and a plural, Q2 becomes the final state. Whereas what about irregular plural and singular nouns? You just move from Q naught to Q2 because there cannot be any specific rules for it. Here, goose has become geese, whereas sheep is being retained as sheep, mouse has been retained converted to mice. So there are not probably rules which can depict each and every irregular singular noun and plural, and therefore every word is explicitly taken from the initial state to the final state. Now we'll move in for the verb. We'll take it from, I think, yeah, it's here. Now this is where we, okay, this is where we take the regular verbs from. Regular verbs, if you just take, you have stem, you can either have an S form or an ing form or a past and participle. Whereas in irregular, you have one, two, three, four, and 5 different forms. That is what is incorporated over here. A regular verb stem, you can, this is the stem word. You can, by reading it, you can reach the final state. Now, either I can add and past participle or in past you can add an ed to it. I'll move on to the uh, state. Now what happens to an irregular one? Irregular one has different forms, so ing with so on and so forth. All these three, the regular verb stem irregular verb stem, the participle verb, and everything with you where you add ed, ing, and yes is will represented over here. So you have three final states. Regular verb stem with ing, these two are being taken together. Where ing is being considered, it is moved on to Q3. Where you have either your past tense or past participle, it moves on to Q3 again. Irregular verb, we don't have any options. You have to specifically spell it out one by one, and therefore you take it from Q0 to Q3. And then here you have something on adjectives. Now, adjective root is from Q1 to Q2. Sometimes I would have an prefix, sometimes I would not have an prefix. Uh, the Can we talk about, okay, let me take unhappy, happy, and happiest and unhappiest. Okay, these are the four words. Now, what happens? Happy is an adjective which doesn't have an prefix and a suffix. So you move from Q naught. Q naught, you have two transitions. One is on UN and the other one is on epsilon. What does epsilon mean? Epsilon means it's an empty string. By reading no character or no prefix or no suffix in general, by reading no morpheme, I can move from Q naught to Q1. And therefore, if I don't have a prefix attached to happy, I'll use this epsilon to move from Q0 to Q1. And then adjective root is happy. So by reading happy, I move from Q1 to Q2. And I don't have any suffix to it. And therefore, we have reached the final state. The output is happy. We are talking about happiest. So it moves from Q0 to Q1 again on epsilon. The adjective root to Q2. There I don't stop now. And because I have another morpheme which is an suffix which talks about est. By reading est, y gets converted to I and you move on to Q3. Whereas the next two has a prefix to it. So instead of for unhappy and unhappiest, instead of using epsilon, I will use the UN transition, which talks about and. So prefix is being considered, and then you have a root word which is happy. Either you stop with it or you go ahead with the next suffix, you end up in Q3. So this is how every information is being taken into account. Sometimes we'll have more adjectives. So what have they done? And they have talked about certain adjectives. These are both root one. Either they follow the prefix or they don't follow the prefix. And once they are in Q2, you can combine with er, ly, and est. You have set of other adjectives uh, which will never have an prefix at all. Okay. So now what they have done here is they have taken two different adjective formats. One, in this case, uh, I'll talk about big. Okay. This allows unbig. Unbig is also allowed. Hope you will be able to understand it. One second. Hope you understand it. I'll just repeat it with an example. Now we'll just take this part alone, okay? We'll talk about happy and big. Let's not talk about any other informations. And we'll try to understand why they have gone in for a new concept or a new diagram. Okay. Now we'll go ahead with happy. I can have unhappy, that is allowed in the vocabulary. So how do I define unhappy is this way. Start with Q naught. Okay, hope you are able to see all these what I'm writing. You have unhappy, you start with Q naught. Q naught on reading UN, you move to Q1 and the adjective root is happy, there we end. That is Q2, that is your final state. If I have happy as such, I'll go to Q naught on epsilon. You don't read anything. Okay, so I'll insert epsilon as such. Yeah. On reading epsilon, you move to Q1, and then you end with happy, you end up in Q2. Now, when I have a word big, uh, you start with Q naught, with epsilon Q1, and then you have big, end up in Q2. Now, my question is, this transition is a correct transition, okay? You from Q naught. Big happy is one adjective, big is another adjective. Now, when I take this part, this is allowed. As per your diagram, this is allowed. From Q naught, either I can choose UN or I can choose epsilon. If I choose un, then what happens? I end up in deriving a word unbig. Is it allowed? Do we have unbig in the vocabulary? Can I have an yes or no from your end? Those who say yes can raise your hands. Do I have the keyword unbig? Okay, the keyword unbig is not allowed, but my transition, my diagram, or the finite state machine allows a word which is not in the vocabulary. And therefore, now I divide them into two different roots. A root where a prefix can be added, and a root where a prefix cannot be added. So in this case, how does it work out? You take Q naught. If it is a root where prefix can be added, it goes through this way. That is root 1. And then you have epsilon. If it is an adjective root 1 where prefix can or cannot be added, it goes through this way. If a prefix cannot be added at all, then I take it to the next root. You have Q0, Q3, Q4. There you end, and then you have all the other suffixes to be added. Fine. So now what have we done? We'll go step by step. We have talked about nouns. This is where you talk about a common simple example. Then you talk about noun. We have talked about verb. We have talked about the adjective. Now, if I have to combine these things, I have to do a lot and lot of analysis. Now, this is just for derivational morphology, where the previous ones are for inflectional morphology. Fine. So this is again for derivational morphology, where you have a noun. When I add IZE, it becomes a verb. When I convert it to ATION, it becomes a noun. So a noun gets converted to a verb. On adding able, it becomes an adjective, so on and so forth. So this represents a derivational morphology. Fine. So this morphology helps us to identify the subparts of your word and find how does it work. Then you have the finite state machine. Finite state machine, you can also put it in this way. The lexical way is for cats, you take it as this is a tape. That is what they normally call it as in a finite state transducer. You have a tape, will be able to read characters from to it. So on surface, you have cats. CAT is the root word, so we have put it as such. And then now I have recognized this cat as a noun. So the second term following cat would be plus n onto your lexical perspective. What is a lexicon? Lexicon gives you the details of the instance what you read or the morpheme what you read. And then we have taken cats. When I read the end of the noun cat, it says that it is a cat which represents a noun. And then you have one more character to read. When I read this character, PL, it indicates that is a plural form of it. So now to understand this finite state transducer FST helps us to map one symbol with the other, and then you move on to define the languages which can be recognized by these finite state automata. Now, for example, if I take this finite state automata, finite state transducer, you talk about fox, cat, cats, dog, dogs, monkey. You talk about names which are being represented. Now, this all the set of strings or words which can be represented by a finite state transducer which you have generated, put together, you call it as a formal language. Okay, so finite state automata represents a formal language, and the transducer helps you to define the relation between the set of strings where you talk about a noun, you talk about whether it's a plural, singular, verb, adjective, how does it get translated, so on and so forth. So you have four ways in which you think about the transducer. We have talked already about two things. One is finite state automata, or you call it as finite state transducer as recognizer. This is also called as the acceptor. Now it takes in a pair of strings, uh, checks whether it is accepted or it is not accepted. So that is, you call it as a generator. Now having a pair of strings, you can always go ahead and generate a new output. Now that is generator. Reading a set of string, when you say cat, noun and plural, it generates a complete new string where you call it as cats. When you talk about computer, adjective IZT and ATION. From computer, a new string has been generated where you call it as computerization. So now what has happened? You really take a word, convert it into a different word, you call it as a transducer. So you get an input, you have a set of outputs or one output. And then finite state transducer as a relator. It tries to compare or map one set of words with the other set of words based on certain mappings what are provided to us. Now, in general, we have seen a set of states. Am I right? These set of states or nodes are called as the set of states. That is the first one. How do I define FST? The first part is Q, which are the nodes, which represents the set of states, and the characters on the edges, which you call it as a set of symbols, which you call it as sigma. Sigma is a finite set of symbols which helps us to map the input and output pair. On reading A, the output would be A if it becomes a transducer. And the initial state is Q naught. Finite state, you can have multiple finite states. Throughout the examples, what we have seen, if you just recollect it, we would have got a single initial state and multiple final states. So F is a set of a final set of final states, which is a subset of this set Q. And you have the transition from a particular state on an input, it produces a particular output and moves on to a different state. Yeah, so that is how it is. Here you read B, A, and then you have the sigma. So these three are the symbols. On reading A, you retain it as A. B is retained as B. Exclamatory as exclamatory. A, if it is there, you have other options. A can be converted to exclamatory, or it can be ignored where you replace it with an empty string, or if there is an empty string, you can always bring in an exclamatory to it. Fine, there are two more things which we have to understand. The first one is inversion. If I could map cat to cats with the help of finite state automata, I can also map cats to cat. The reverse or the inverse of it is allowed. Okay, that is the simple example of inversion. If I could map cat to cats, that is from singular I am mapping it to plural. The inverse of it from cats to cat is also allowed. That is what it says. If T maps, if a transducer machine T maps the in I to O, the inverse of T inverse maps from O to I. Now what about composition? Composition is where you have a transducer which maps from I to O, and then you have a transducer which maps to I2 to O2. If these two are brought together, okay, then you can map from I1 to O2. Uh, we'll see this way. You have a mapping where you have a regular noun, and then you have a particular noun here. Now, if I could map from Q0 to Q1, this becomes one state transducer, and you have another output. Now, I can take this and move till to this part. So, you have a composition which takes in two transducers and replace it with a complex transducer. Easy way of understanding. If I could have add two numbers using a finite state automata. Okay, is that allowed? That is allowed. And if I could also check if the addition, if the numbers to be, or I'll put it in this way. Mm, if I have to subtract two numbers and I ensure to subtract x and y, x has to be always greater than y. Okay, so now what do? You check, you have a function. We'll put it this way. I'll just write it and then we'll move ahead. If I have f of x, okay, f of x is a function which is 0 if x is less than y, and it is x minus y if x is greater than or equal to y. Now, what happens here? Uh, you do a function, but what I need is I need a subtractor and a decision maker. Okay, so now what has happened? This is one finite automata, this is another finite automata. So I have taken two different finite automata and combined together to define f of x as a complex job. That is what they try to do it here. You take f of, you take the complex ones and then you convert it to a normal one. So now here you have just examples where a transducer maps things in noun stem, you have mapped it, and once you reach the final state on reading any inputs, you are there in the final state. Okay, you have a transducer where you have morpheme boundary and a word boundary. What is morpheme boundary? For fox is a morpheme, so I have a morpheme boundary. When you have plural, when you end the complete word, you have a word boundary. So you can also separate that way. Every morpheme, a prefix or a suffix or every unit can be separated by using the morpheme boundary, or else we'll do it with a word boundary. Fine, you have certain rules. You have all these are just explanations of examples of how it works on. So if you just look at here, you have on the surface it is foxes, and then you make them into this is the input what we see. But how does it work on this? They divide it into morphemes. One is fox, a morpheme boundary, and yes, now this fox is considered as a noun and then followed by an plural part. Now the rules, how do I represent? Okay, now we'll just take this here. A will be converted to B in a word if it occurs between C and D. That is how they expect. Okay, A will be converted to B, not always. Always when you read A, it is not converted to B. The condition is it has to occur between C and D. So similarly, where empty value can be converted to E if and only if we have X, Z, and X, S, and Z, and followed by a plural, and here you have a word boundary. Hash is a word boundary. So if I have a word which ends with X, S, and Z, and I have a plural of it, I'll be inserting E to it. Now you talk about fox, and you have a plural yes. When I have a plural yes, what am I supposed to do? This is a word boundary, so I have a hash over here. Now fox, the last character is X, so I don't have anything between X and this yes, and therefore I call it as an empty string. This empty string appears over here, and then it gets converted to E because of this rule what is given to us. Fine. So such kind of rules can be written. We'll talk about how these things can be taken into language modeling uh, by using various statistical models in the next class. If you have any doubts, you can ask me.